Hi guys. So in this video, we're going to address the last question as far as those three questions about kinetics go, which is knowing if a reaction will occur spontaneously or not, meaning will it happen all by itself? Is it likely to happen without being like forced? So, in order to decide if a reaction will be spontaneous, we have to know if it's exothermic or endothermic, and we've talked about that a lot over the past couple of days. But there's this new word, entropy. We have to know what's going on with the entropy of the molecules in the sample. And entropy is like its messiness. A word you'll see used is disorder. So you almost want to like imagine a particle diagram and think, which of these is more messy? That's the one that's going to have more entropy. So there are a couple different ways we can increase entropy. In this first example, I have water, right? So I have the liquid phase in both examples, but here I have cold water and here I have room temperature water. Notice that when you increase the temperature of a sample, the particles move around a little bit more and they spread out a little bit more. So anytime you increase the temperature, you're going to increase entropy. You're going to make the particles behave a little more randomly. Okay. As far as actually changing the phase goes, going from solid to gas, you're increasing entropy. Our solid is our most organized phase, so entropy is very low. And as we go to a gas, we're getting more and more random. I would say solutions, so something dissolved in water, would be similar in entropy to the liquid phase. They'd kind of be the same. The last thing you can do, guys, is look at the type of reaction. If it's going to be a decomposition reaction where you start with one thing and you're breaking it up into pieces, you're going to be increasing the entropy. Okay. Think about building a house out of Legos versus breaking that house apart and throwing the Legos everywhere, right? Which one of those scenarios is more messy or is more disorganized? The one where the Legos are all over the place instead of clicked together in one big house. Okay. So any of those things going on could be telling you about entropy. So how does this tell us if a reaction is spontaneous or if it will occur naturally? I want you guys to think about a typical teenager. I know I'm going to offend some of you, but typically we're lazy, so our room gets messy. Think about getting ready for school in the morning. You put on an outfit, you hate the way it looks. 99% of us are going to take that outfit off and throw it on the floor and get a new outfit because we don't have time to fold everything back up and put it nice and neat in our drawers, right? It's easier to throw it on the floor in a ball than to make it nice and neat and put it back where we found it, right? So if you think of being lazy and that leading to a messy room, that's like what happens in nature. You can also think that way about a chemical reaction. As far as energy goes, what type of energy is associated with being lazy? Less energy, exothermic. If a reaction is exothermic and the products have less energy than the reactants, that reaction is going to be more likely to be spontaneous. And the other part, messy room, we want entropy to be increasing. That's more likely what's going to happen in nature, right? So if both of those things are present, the reaction will definitely be spontaneous. Not to say that, if you have one and not the other, it might happen. Similar to like applying to college, right? There's like a whole list of things that you guys want in order to get into a good college. You want good grades, you want to have extracurricular activities, you want to do volunteer work, you want to have good SAT scores, right? A whole list of things. But if you only have like 8 out of those 10 things, can you still get into college? Of course. But you have a better chance if you have all 10 of those things. So it's the same thing here. Having both of these things happening will definitely lead to a spontaneous reaction. But if you have one of them and not the other, then it depends, okay? So delta S represents change in entropy. Don't ask me why S is the symbol for entropy. Okay, so if I want to find delta S, the change in entropy for a whole reaction, I want to do, you've seen this before, the sum of the entropies of the products minus the sum of the entropies of the reactants. Okay, now I want to show you guys a table if I haven't shown this to you yet in class. This is going to be posted and it's available for you to use. But this table gives you the heats of formation of different compounds. It gives you the Gibbs free energy of different compounds, which we're going to get to at the end of this video. And it also gives you the entropies of different compounds. So the numbers that I'm going to use in this video, I'm looking up on this table. I don't want you to think you need to know those. Either you're going to be given them or you're going to be given this table. It is nice that the compounds are kind of grouped based on elements they have in common, plus it goes in alphabetical order. So anything you need to find is on here. What you do need to be careful about, I want to see if I can find one off. You need to be careful about elements that look very similar to each other. They differ by one letter. And you also want to be careful about phase. Like here's water, but all of the values for water in the gas phase are different for all the values for water in the liquid phase. So you really need to use this chart carefully. I'll say that. All right. So let's do the reaction that we've been working with this whole time, which was my my propane reaction. So I have propane, 5 oxygens, and I'm making 3 carbon dioxides and 4 waters. So we've seen this reaction now a bunch of times. Now, instead of looking up heats of formation, I want to know what the change in entropy is. So I want to be looking up the entropies of all of these things. I would love if you guys could pause the video. I'm going to give you the phases here, just in case you need them. This is a 5, not an S. I would love for you guys to go look up these values on the table that I just showed you, just to make sure you're getting the same values as me. And then when you come back, we'll plug in some numbers together. Okay. All right. So hopefully you actually did that. I'm sure some of you did. But I got 269.9, 205, 213.6, and 188.83. So guys, if you looked up something just different, just go back and check that chart, please. All right, so let's plug it in. All right, now I have products first. So 3 carbon dioxides plus 4 waters minus 1 propane plus 5 oxygens. Okay, please, please, please pause the video and calculate this yourself. I will be writing the answer here. You want to make sure that you're plugging it in the same way I am. Okay, now guys, as far as our units go, if you look at this table, you're given units for every single thing you might have to look up. So we're just like adding and subtracting here, multiplying. Our units are staying the same. So since this question is about entropy, my units in my answer would be using those entropy units. So it's joules per mole Kelvin. All right, now you might have to convert to kilojoules at some point. Later on, this delta S is going to be part of a bigger reaction. And if you look at this table, the heats of formations and the delta G, the Gibbs free energy, those are all in kilojoules. And you can't be putting things in the same formula that have different units. So that the entropy is the one we're probably going to just convert, because then the other two are already in kilojoules. But we'll get to that later. What I want to talk about is what this all means. When you calculate delta S, if you get a positive value, that means that entropy is increasing. So if I want to know, I got a positive value here. So in this reaction, my products are more messy, they're more disorganized than my reactants. So is there a chance that this reaction is spontaneous? Yes. We already know it's got the increasing entropy piece. If it's an exothermic reaction as well, then we're in good shape, and we're probably going to be a spontaneous reaction. Okay? So Gibbs free energy, which is this delta G that I've been talking about, this actually lets you calculate if a reaction will be spontaneous or not. So in those scenarios where you have one and not the other, maybe it's exothermic, but entropy is decreasing, or maybe it's endothermic, but entropy is increasing, you could actually use this formula to decide if the reaction is going to be spontaneous or not. So delta G, which is Gibbs free energy, the formula is delta H, which we know already is heat of reaction, and we know how to calculate heat of reaction, right? So that we already know. Minus the T is temperature, and the temperature has to be in Kelvin, and delta S is our entropy. So here is where they all come together in one reaction, and our units are going to matter. What you could do also, guys, and this is just like a side note, I'm going to say that same reaction that we've been looking at over and over again, if your reaction is happening at 298 Kelvin, if the temperature is the same as what's on this chart, then you can just look up all the delta G values for everything in the reaction, and you can do, just like we've been doing, the sum of the products minus the sum of the reactants. And that will give you the delta G and let you decide if the reaction is spontaneous or not. If the reaction is occurring at any other temperature, then you have to use this formula. So I'll write only for 298K. And we want to use this formula for any other temperature given. So for this kind of question, you'll have to be given the temperature. After you plug in numbers and do this calculation, if your delta G is negative, that means your reaction is spontaneous. If it's positive, it's not spontaneous. And if it's 0, that means we're at equilibrium. So both the forward and reverse are going at the same rate, and we have everything staying constant. Nothing's really changing. Okay, so let's take a look at this chart. Reactions occur spontaneously if. So we already said we want a decrease in energy, we want it to be exothermic, and we want to increase entropy. We want to get more messy. Those are the two requirements, right? So as far as this chart, it's just showing us what we already talked about. If delta H is negative, that means it's exothermic. And if delta S is positive, that means you're increasing entropy. That means you're going to get a negative delta G, and you're always going to be positive. If it's the opposite, if delta H is positive, you have an endothermic reaction, and T delta S is negative, meaning you're getting more organized. That doesn't have either one of my requirements, so that's never going to be spontaneous. Delta G will come out to be positive. Okay? Now, here's where things get messy, right? I have a positive delta H, endothermic, and I have a positive delta S, increasing entropy. This is good. This is bad. So we need to decide if this is enough for the reaction to be spontaneous, because the answer is that it's only spontaneous sometimes. It's only spontaneous if the temperature is high. If the temperature is high, then this value is going to be big. And if that value is big, you're subtracting a big number from a smaller number, your delta G will end up being negative and the reaction will be spontaneous. Okay, let's take a look at another example. Here I have XO, and here I have decreasing entropy. So the opposite of the one above. This is good, this is bad. But still, the reaction sometimes can be spontaneous. If the temperature is low enough, then this value is going to be low. And I'm going to do a big negative number minus a small positive number, leading us to a negative delta G, meaning it could be spontaneous. So you guys are required to know which type of temperature is better when both requirements aren't there. All right, so let's do one more example together. This is a biggie, guys, because I have to do everything. My formula for delta G is delta H minus T delta S, right? So I need to do delta H first, meaning I have to go to this chart and I have to look up the delta H's, the heats of formations of everything in that reaction, right? And I have to do products minus reactants. Okay, so if I look up carbon dioxide, there's 2 of them, and the H's are negative 393.5 plus water. Oh, I didn't balance the equation. Sorry, guys. You do have to balance it if it's not balanced. There's 2 waters, and water has a delta H of 188.83. All right, minus reactants. Oxygen is 0 because it's an element, so I'm just going to do butene here, which is 52.30. And I have one of them, and I'm going to get negative 1322.94 kilojoules per mole. How do I know the units, guys? If I look at this chart, delta H's are kilojoules per mole. All right, I'm going to do delta S next. So again, I have to look up everything on this chart, and I have to do products minus reactants. So, whoops, I'm writing delta H twice. I would love if you guys are pausing and looking up yourself. If not, you're going to get it in class tomorrow, but that's where I'm getting these numbers from. Again, I have 2 carbon dioxides. Each one has an entropy of 213.6. I have 2 waters. You know what I'm noticing, guys? I did this wrong. I copied the S value where the H should be. See? Make mistakes all the time. This should have been negative 241.82. Sorry about that. This is 188.83. Okay, now I have to do my reactants. All right, so I have 1 butene, 219.4, plus I have 3 oxygens. So elements are only 0 when it's the delta H. If it's S or G, you want to be looking up those numbers. All right, now if I'm copying units from my table, joules per mole times Kelvin. So see what I'm saying, guys? I have kilojoules and joules in the same equation, so I can't do that. I need to change the joules to the kilojoules. All right, so delta G equals delta H, negative 1322.94, minus temperature has to be in Kelvin. So if they gave me negative 10 degrees Celsius, I'm going to add 273 to that, and I'm going to get 263 Kelvin times, if I move the decimal 3 places to the left, I get 0.02954. And if I go from here, I get negative 1322.94 minus a negative 7.77, which turns into plus a positive, and I get negative 1315.17 kilojoules. Okay, so is this spontaneous? Yes. How do I know that? Delta G is negative. Okay. If you're solving for temp, make delta G 0. All right, so that's it for kinetics, guys. We will spend tons of time practicing, and I will see you next time.